Hello again, my dear students, and welcome to the third part with our atomic radiation chapter, chapter number 3 in the optical system course. In the previous part, we have reached this general form for the rate equation for a two-system model, where we have reached what we call the stimulated emission cross-section, sigma. And we substitute this sigma in the rate equation so that we have dN2 by dt is equals to negative A21 N2, which represents the spontaneous emission due to an independent frequency term. Then we have the term sigma I mu over H mu times N2 minus N1 G2 over G1, where N2 represents the stimulated emission process, and N1 G2 over G1 represents the absorption process. Now, what we are going to do in this chapter is that we are going, or in this part, I'm sorry, we are going to reflect this equation on a system. So let's now start to describe the system where we are going to reflect our rate equation on. Okay, so what is our system? Our system consists of a light source. And as I mentioned in part number 2, we will assume that we have a laser source as an incident light source. This laser source induce or transmit a light or a photons with an intensity I mu to a certain material. The material has a thickness delta Z. Once the material, here of course we will conclude the material as a two energy level as we did. So we have an output intensity, which we call it I mu plus delta I mu. And in order to detect this intensity, we have a detector with an area delta omega, and we have a certain bandwidth of frequencies that we will receive, which is plus or minus delta mu over 2, and we have a polarizer to detect the polarization of the output. So it's very simple experiment, a source and a detector and a material in between. Generally speaking, my dear students, we should expect that the three processes will occur inside this material, because simply these three processes are the main three probabilities we define. And as Einstein mentioned, practically speaking, we have very huge number of probabilities. However, we assume that these three processes are the most significant or the major processes in the two-level system. So we have three processes, what we call the spontaneous emission, absorption, and stimulated emission. What we are going to do now, my dear students, is that we are going to try to describe the output term in terms of these three processes, because what you will get in the output is either a stimulated emission photon, a spontaneous emission photon, or you will not get a photon due to its absorption process here. This is the three probabilities. So these are the three probabilities we have in the system. Okay, so how we are going to write this equation? Let's try to describe it together. First, let's start with this. Of course, we have to agree that we have two factors that will contribute to the detectors, which is stimulated emission and spontaneous emission. So whenever you detect a photon here, I mean, with each added photon here in the plus sign, this photon may be a stimulated emission photon or a spontaneous emission photon. And whenever we have a photon which is emitted by the source, but we didn't detect it in the receiver, then we will say that this photon is absorbed by the system. That's why we have two positive signs and one negative sign. The two positive signs stands for the stimulated and the spontaneous and the stimulated. However, the one negative sign stands for the absorption. And all of these have an energy called H mu, which is the energy for a two-level laser. Then, regarding the intensity, let's start with the third row, which represents the spontaneous. Of course, I know that it's spontaneous because we are using A21, which is the coefficient for the spontaneous. So we have A21. But as here we are only detecting photons with a bandwidth plus or minus delta mu over 2, so it's delta mu. So we multiply this A21 by delta mu. Because generally, in the spontaneous emission, you can produce photon with any type of frequency. But due to the limited bandwidth of the detector, you will only receive the photons which has a delta mu variation with respect to H mu. So this is the bandwidth of your received photons due to the spontaneous emission. So this is about the spontaneous. For the stimulated emission, for the absorption, you have B21 times rho of mu. So rho of mu now it's I mu over Cn, which we already define it if you remember in part number 2. I mu over Cn, this is rho of mu. And then here, again, we have H mu times B21 I mu over Cn, which is again rho of mu. Because if you remember, the stimulated emission and the absorption are rho of mu dependence, if you remember. Here we have G of mu, which is aligned with function, of course. Here we have the polarization. So all the photon produced from the source and have a coherent photon due to stimulated emission, one of the definition of the coherent photon that the produced photon should have the same polarity like the incident one. So as far as the photon is stimulated, its polarity will be 100% the same like the incident photon. Similarly, in the case of absorption, the missing photon, which is an incident photon, of course, have the same polarity of the source. So now your polarizer will collect 100%. And here your polarizer will not collect 100% because this is absorbed. However, for the spontaneous emission, it's a randomly generated photon. So it can be an S polarized or a P polarized. Accordingly, if your detector is S, you will collect only 50%. Or if your detector is P, you will only collect 50% because it's a randomly output. Accordingly, you will collect only half of the incident photons. What about the area? If it's a stimulated emission photon, then it's 100% in the same direction of the incident light, because again, this is one of the restriction for stimulated emission. So if I'm assuming that it's a perpendicularly incident photon, then the stimulated emission generated photon should be also perpendicular. So it will be collected by the detector by 100%. And if it's not a transmitted photon, I mean, if it's an absorbed photon, of course, it will not be collected. So one again. However, if it's a spontaneous emission, it can be random. So it can be in this direction, in that direction, in this direction, any direction. So what you are going to collect is only what is your area, which is delta omega, over the overall area, which is 4 pi. If you remember the overall surface area for a sphere, which is 4 pi, I believe you already see this term before in the antenna, whenever you have an isotropic antenna or an anisotropic antenna. So this delta omega represents the area of the detector with respect to the overall isotropic profile of the spontaneous emission, because in the spontaneous emission, your emitted photon can be anywhere. can have any direction, but you are going to collect only the photons that are located in this area. So you are collecting delta omega over 4z. And finally, what is the total number of carriers we have, or the number of electrons? So this is n2 times the distance, which is delta z, and this is n1 times delta z, and this is n2 times delta z, because basically in the spontaneous and the stimulated, your stack is n2, and in the absorption, your stack is n1. So generally, this what the is delta I mu, or the variation that will happen in the intensity. And it makes sense that if the absorption dominates, this delta I mu will be negative. Then you will, for example, transmit 100 photons, but you will receive only 50, because the absorption process is the dominating process. So delta I mu will be negative, and the output is less than in the input. If it's an equalized equation, I mean, the stimulated and the spontaneous are as equal as the absorption, then this delta I will be equal to 0. If the stimulated and the spontaneous are greater than the absorption, then delta I will be in positive, and then you have what's called a light amplification. So, for example, you transmit 100 photons, but you get 200, then you have delta I of 100 photons. But we have to mention that this is just the summation of the process. I just add all these terms together in one line. That's all. But we have to say that in our case, we are not seeking for an amplification and full stop. We are seeking for a coherent amplification. What I mean by a coherent amplification is to produce an output intensity which is coherent to the input intensity. I mean, we are only searching for the stimulated emission photon, not for both the stimulated and the spontaneous. Accordingly, my dear students, we are going to define this term, which represents the spontaneous emission as a noise. It's an added photons to the detector, that's true. However, it's unwanted added photons, because I need the addition, I need the amplification to be only due to stimulated emission, to have only coherent photons, not spontaneous generated photons, because simply the spontaneous generated photons are not controlled. It can have any direction, any frequency, whatever it is. So what we are going to is that we are going to neglect this term, because it is as unwanted term, and we are going to think about only about this term, which represents the stimulated emission in positive and the absorption in negative. And we will say that this is the central equation of a laser theory. What I did here just is that I substitute by P21 and P12 by their corresponding term in terms of A21. So I got this long equation. If you remember, this is sigma. We have already defined it in the end of part number 2, which is the stimulated emission cross-section, sigma. So we have, yes, we have here this sigma term times 2n2 minus g2 over g1 I of mu. And we will call this big term gamma. Now, this is a competition between the stimulated emissions and the absorption. If the stimulated emission dominates, then your light will be amplified. If the absorption dominates, then your light will be attenuated. So simply, in order to grant an amplification process, which is a one-step toward laser, because remember that laser is light amplification for stimulated emission of radiation. So we have first to amplify light. So in order to grant this laser process, we have to set gamma greater than 1. And as you can see, the condition where you can put gamma greater than 1 is to have N2 greater than G2 over G1 times N1, which we will call it the condition for a gain. So in order to grant this a condition for a gain, in order to be sure that the light that you will collect is greater than the light you have inserted, you have to manage this condition to have the popularity in level number 2 greater than G2 times G1, which are constants related to the density of state, if you remember, times N1. If this condition happens, then this will be a condition for a gain, or between brackets, a condition for a razor. Herein, we will define the term sigma, the original sigma, times G2 over G1 as the absorption cross-section. So simply, my dear students, this is sigma. So you multiply sigma by N2, so this sigma will be the stimulated emission cross-section. If you multiply sigma here, so you have G2 over G1, then we call it the absorption coefficient, the absorption cross-section. So the absorption cross-section is simply equals to the stimulated emission cross-sections multiplied by G2 over G1, and that's all. Simple like that. So this technically is the end of chapter number 3, which is the atomic radiation chapter. However, we have to be quite sure that you totally understand this central equation for laser theory, because we are going to use this equation in the next chapters. And this condition, which is very, very important, related to the gain condition. This is a condition to ensure that the light has been amplified. But as I mentioned in part number 2, before terminating this lecture, I'm going to solve with you one of our solved examples related to the main core of this chapter, which is the line shape function. In this example, we say that the spontaneous emission profile from a certain transmission can be approximated by the shape function shown below. So this is a line shape function. Here, as you can see, we have a unit of centimeter per minus 1. I will talk about this unit now. And we have this line shape function. And they told us that we have 2 levels. This is the first level, and this is the second level. And this is J1 and J2. And also I will mention what is J1 and J2. And we have A21, which is the rate for spontaneous emission, if you remember, equals to 10 seconds per minus 1. And what is required is to calculate the emission cross-section and the stimulated emission cross-section and this absorption cross-section. So let's start with the stimulated emission cross-section. So now let's return to the equation of the stimulated emission cross-section, which is here, A21 lambda square 8 by n square G of mu. This is the same. So let's now go to our whiteboard and start solving this equation. So first, in order to calculate this sigma, that's just searching for the best pen to write. Okay, this one. So sigma equals to A21 lambda square over 8 by n square times G of mu. I think this is right. Okay, perfect. Now let's search about these givens. A21 is already given. A21 equals to 10 seconds per minus 1. If you remember, we say that this A21 is a rate. This is a rate for the spontaneous emission. So its unit is second minus 1. That makes sense. Then, as far as I didn't mention anything about the materials, then we can assume that we have air with n equal 1. So you have n and you have A21. So now we still have two unknowns, the lambda, which is the wavelength, and the G of mu, which is the line shape function. Okay. So what is lambda? Lambda is a wavelength. Wavelength of what? Wavelength of the emitted photon. How shall I calculate the wavelength of the emitted photon? Do I have any given that can be used to determine the wavelength for an emitted photon? Let's see. So I will return back to the question. I'm sorry. Yes. Yeah, this is the question. So if you see here this graph on the left-hand side, we have two energy levels. So whenever you have a photon, that means that this electron is jumps from this energy level to this energy level to produce a photon. And as we say that this happens for this mu node, which is the central frequency or the central wavelength. So now if I get this energy difference or frequency difference or wavelength difference, then I can calculate lambda. But what is weird somehow, my dear students, that what is given here is not energy because its unit is not electron volt. And it's not frequency because its unit is not hertz or second minus one. And it's not wavelengths because its unit is not centimeter. It's something in centimeter minus one. And you can see that this centimeter number minus one appears here in the energy band diagram and appears here in the x-axis. So what is this? We used to have this line shape function with an x-axis, if you remember, indicates the, Yes, we used to have this line shape function with an x-axis indicated in frequency. And as I told you, this may be also energy because energy equals h times the frequency. Or it may be equals to wavelengths because the wavelength is the reciprocal of the frequency with a C coefficient. So mu equals C over lambda or lambda equals C over mu. So you can adapt. You can expect having this x-axis either in energy, either in energy or in electron volt, or in frequency mu, or in wavelengths. But what is given in the question is not energy, and it's not wavelengths, and it's not frequency. It's something given in centimeter per minus one. So we have first to investigate what is this. Okay, so this is, my dear students, is what we call the normalized wavelengths. What is the normalized wavelengths? So as you know, lambda is in centimeter. But if you normalize this lambda over C, you normalize this wavelengths in you normalize this wavelengths with or in terms of a light, then okay, I'm sorry, not the wavelengths. I'm sorry. Lambda is centimeters, that's true, and mu is in second. What if you normalize the frequency? I'm sorry, not to normalize the wavelengths. If you normalize the frequency, so you have mu, which is second minus one, and then you are going to divide mu over c, which is the speed of light, of course. Then, which is centimeter second minus one. So the output unit will be second minus one over second minus one will be cancelled, and 1 over centimeter will be centimeter per minus one. So whenever you see this centimeter per minus one unit, then this is what's called the normalized frequency. This is actually very famous in the numerical solvers for the finite different times domain solution for the Maxwell's equation. Maybe this is something very advanced, but this is very famous in optics and in Maxwell's equation solving for optics, to have a normalized frequency instead of frequency. So what you see now in the x-axis is not frequency, or it's not wavelengths or energy. It's a normalized frequency. So if we return back to the head of the question, we have these two energy levels. And if you read what is written there, you will find that 1840, okay, so it's 18,340 centimeter per minus one. Sorry, minus one. and here is 2627 centimeter per micron. So this and that are a normalized frequency component. So this term is mu over c, and this term is a mu over c. So you can very easily, simply, or very simple, you can turn them to be mu2 and mu1 by easily multiplying these two terms by 3 times 10 power 8. So if you multiply this by 3 times 10 over power 8, you will get mu2 and mu1. But if you remember, my dear students, we are now interested not in mu, we are interested in lambda. So if you think for a while, you will find that the, let's call it mu n, or normalized frequency, which is equals to mu over c, is simply equals to 1 over lambda, because lambda equals c over mu. So just giving 1 over this, so here 1 over mu n2 will give you lambda 2, and 1 over mu n1 will give you lambda 1. And lambda 2 minus lambda 1, or what you are searching for, which is lambda, is equals to lambda 2 minus lambda 1, which is simply 1 over this 18340 minus 1 over 2627. So this is very simple. Of course, you have to make it in the reverse direction, because lambda is the reverse of the frequency. So in this manner, you will find that lambda 2 is smaller than lambda 1, which is expected because mu2 is greater than mu1. So it makes sense that lambda 2 will be smaller than lambda 1. So you can just get the absolute value of this. So this is a very simple way to calculate lambda 2 or lambda 1. Of course, you can make it in another way. You can say that it's mu2 minus mu1, and then you get what's called mu node. And after you get mu node, then you can say that lambda equal c over mu node. And then you get this term. Of course, mu2 equals to mu n times c, and mu1 equals to mu n1 times c. So this is direct substitution, and you can get lambda node, or the linear lambda. So now you know 8 to 1 is given, 8 by n square known, lambda square we know lambda. Then what's remaining is g of mu. What is g of mu? Okay, if you return back to the question, to the head of the question, again here, you will find that we already gave you this g of mu function. And as usual, we are searching for the maximum probability at mu node, which is k. But how can we calculate this k? Okay, let's see. You have a very known knowledge or information about this curve, that the total area under this curve should be equals to 1, because this is a probability density function. So if you sum the total area here, this total area should result to 1. Let's do it. So we have a function like that. This is mu node. This is -3 minus 4. And this is 1. And this is centimeter per minus 1, which is again the normalized frequency. And we have something like that. Okay, sorry. So this value is k over 3. And this value is k. Of course, my plot is very bad not to scale. Maybe in the question it's to scale. But you don't need scale to calculate it. What you are seeking for is the area under this curve. So the easiest way actually to say that this, let's make it in somehow in calorie. So we have a triangle. So we have a triangle. And then this is can be like this. Okay. Okay, this is the easiest way. Just like the when kids starts to play and divide any shape into rectangles and triangles. So we have this triangle first, which has, of course, the area of a triangle is half the base times the height. So it's half the base minus 3 minus 4, which is 1, times the height, which is k over 3, plus this rectangle, that the length and the width. The length is minus 3, 0 minus 3, which is 3, times the height, which is again k over 3, plus this is another rectangle, sorry, another triangle, then half. The base is 3, and the height is from k over 3 to k, so it's 2k over 3. Then we have the final big triangle. Its base is 1, so half. The base is 1, and the height is k. This will be equals to 1. So simply half k over 3, then we have here k over 6, plus 3 will go with 3, then we have k, plus 2 will go with 2, and 3 will go with 3, so we have k, plus k over 3. This equals to 1. Of course, a very easy equation where you can calculate k. Now, this k represents the j of mu node. So what you are going to do is you are going to calculate k from this equation and substitute by this k here. And then you will get 0. Why you will get 0? Because this g of mu is defined when the x-axis is mu and you have this function, then this is g of mu node, or the value of the g of mu as the central frequency. But now, in the given example, your x-axis is centimeter per minus 1, not mu. So, if you remember, my dear students, I told you that whenever your x-axis is mu, which is a second minus 1, your y-axis will be second, so that the area under the curve will be equal 1. So this g of mu should have a unit of seconds. But now, this g of mu n, or g of normalized frequency, does not have a unit of seconds. Actually, knowing that the x-axis has a unit of centimeter minus 1, that means that this k have a unit of centimeter. And in order to substitute with g in your sigma function, then what you are going to use is that you have to have a g of mu in terms of seconds. Then, after calculating k in centimeter, you have to transfer it somehow to seconds, which is very easy, by the way. Why? This k is in centimeter, and I needed to make it in seconds. What should I do? It's very easy. What you are going to do is that you will make it 1 multiplied by 1 over c. This c have a unit of a centimeter over second. So whenever you multiply this k with 1 over c, which is the reverse process of the normalization, then you will have an output unit of centimeter, which goes 1 centimeter, and then this will be second. So you have to have this step before going to substitute in the equation, because the g, which is the line shape function you are going to substitute with, should be in g of mu, or in seconds, not in centimeters. So this is a very good and important trick here. So now you get sigma. And finally speaking, you need to calculate, this is, of course, this sigma is the stimulated emission cross-section, which we call it sigma CT. So as we say, that sigma absorption is equal to sigma CT times G2 over G1. But if you return to the head of the question, what I am giving to you is what's called J1 and J2. J1 and J2 is called what's called the quantum number. So there is a very famous equation, you can find it in the script, saying that ZG equal to J plus 1. So you can easily calculate G2 and G1 from J2 and J1, and then say that this sigma absorption equals to the sigma stimulated emission, which you will calculate from this equation, and then multiplied by G2 over G1. So you get sigma absorption. And this will be the end of the solution, and as well as the end of the chapter. So now we have terminated chapter number 3, which is the atomic radiation chapter. In this chapter, the main output is to understand what is the line shape function, the different ways where you can see the line shape function, either in frequency, energy, wavelengths, or normalized frequency. Also, we have concluded the central equation for laser theory, where we have found the condition for a gain in order to have an amplification system in our light system. So this is the termination for lecture number 3, or chapter number 3, entitled by atomic radiation. In the next chapter, inshallah, in chapter number 4, we are going to introduce what's called the optical cavity. See you in the next chapter, and bye-bye.